So now we're going to be in chapter 26. Welcome to unit 9. This is the second to last unit of the whole course. We're now halfway through the entire E&M part of the course. This whole unit is about circuits, and we're going to be looking at circuits with resistors. We're going to be looking at Ohm's law, V equals IR, all that kind of stuff. And then towards the end of this unit, we're going to have resistors and capacitors in the circuit. We're going to see how those types of circuits work. So here we go. Let's start with some basic definitions. We have electrical current. It is the stream of moving charges. Conventional current is the direction that the positive charge moves. But positive charge, we don't have like positively charged particles that are moving. We have the electrons moving. Electrons are negative, and so therefore wherever the holes are, a hole is a positive charge, right? The lack of electron is a way to create a positive charge. It's the direction that the positive charges or the holes are moving. So it's the opposite direction of the electrons. That's conventional current. Steady state is where we have a constant current flow over time, so the current's not changing. Charge carrier density is the number of charged particles available per unit volume. Right? However many particles there are that can carry a charge in the volume that's there. Current density is a vector quantity that tells you how much charge is flowing through a particular area, like a cross-sectional area. And then drift speed is the actual linear velocity at which those particles are moving. And it's really quite slow. If you have electrons moving, they're bouncing throughout. So they're actually, in terms of their overall progress, it's very slow, moving from one side of a wire, one end of a wire to the next. And so current. Current is dq dt. It's how much charge is flowing per time. The current density, by the way, J, is where we then multiply that by the cross-sectional area. Or rather, divide it by the cross-sectional area. Divided by the cross-sectional area. And so delta Q, we can think of it as adding up all the charge, and that is I dt, right? If you take current and multiply it by time, that's the total change of area. And if we have constant current, then it's just I times T. And so I equals Q over T, and the current, the unit for current is amperes. An ampere is a coulomb per second. 1 coulomb per second. And then Ohm's law, so in the next slide, again, conventional current is shown the opposite direction of the moving electrons. And Ohm's law is I equals V over R. Voltage, potential difference divided by resistance. We're going to see the derivation of that later on in this lesson. Okay, and the other one is conservation of charge. This was a big thing when we were working with capacitors. It's a big thing now too. Charge has to be conserved. We can't have charge magically created inside of a, inside of some circuit. We can't do that, at least. We've never seen it done. And so whenever we're dealing with charge, we know that the amount of charge there has to be conserved. So therefore, when we have current flowing into and out of a junction, so into and out of some wires, then the total current in has to equal the total current out of that intersection or junction. And so now we have this problem. And so now we've got this whole thing, and some of these are filled in, some of them are not. Notice here I've got 2 and 3 coming in. That means I've got a total of 5 amps coming in. So that means I have to have 5 amps going this way from there. Notice I've got 1 and 2 both coming away from here, which means I know I need 3 amps going in that way. So if I've got 5 amps coming in here and 3 amps going that way, I need to have 5 amps total coming out. So that means this is 2 amps coming down this way. Right? So I've got 2 and 4 coming in. That means I need a total of 6 coming out. So this is 6 amps. And then 6 amps, going that way. 6 amp going that way and 2 this way, then these two add up. And here, this I is 8 amps that way. Okay, so that's that sample problem. 26.3, the current density J. You're not going to see a lot of problems with this, but you will see some. Again, the idea is that we've got the amount of charge flowing per cross-sectional area. And the way we can calculate that is V and Q. You see there's a little demonstration there, like a little piece of the wire and the charge going through. And in the next slide, we can see it as an integral. If J is I divided by the area, then the current is going to be found by taking the current density and multiplying it by all the little pieces of the area of the conductor where the current is flowing. We add all that up, and then you get what the total current is, the total amount of charge flowing per second. And if J is uniform and it's parallel, right, because it's a dot product, then J is I over A. Really simple. For these other two slides are for information purposes only. It says that at the top of the slide, so keep that in mind. The charge carrier density, N is the number of electrons per cubic meter, and that's what the N is in that other slide, V and Q. N is the number of charges per cubic area, so it's 1 over meters cubed. So now graphical analysis, current density versus electric field. Different materials, when you place an electric field across them, you'll get a different current density happening, right? So if we take a graph, current density versus electric field, and then as you change the electric field, you can see what the current density is. If that line, if that function is a line, then we say that it's ohmic. Okay? Ohmic is basically, when we're talking about what creates an electric field, a potential difference, and what is allowing or not allowing the charge to flow, that's the density, and then the result is the current. So what are we talking about here? Basically Ohm's law. We're working towards Ohm's law on this level. And so we end up with this equation. The thing you fill into the box here is J equals sigma E. So it looks like this, where sigma is the conductivity of the material. In other words, how well it conducts electricity. And this is the Joe equation, right? It looks like it says Joe, but it doesn't, because that's not an O, it's a sigma. And so you can see the conductivity for some different materials. Things that are conductors have a high conductivity, insulators have a low conductivity. It's a measure of how well the material allows charge to flow. But the next page, Ohm's law, again, we fill in the Joe equation, but the reciprocal of this would be rho. So rho is 1 over sigma, and rho is what we call the resistivity. It's not the resistance, because the resistance is different for different geometries, but the resistivity tells us how much that material blocks charge from flowing. Think of it that way. And we'll use that in calculating the resistance, which you'll see in a little bit. And then you've got a couple of tables. Resistivities at different temperatures, and that brings us to the next graph that you see there, resistivity versus temperature. And you can see that it's almost linear, and so we're going to treat it as linear. As we change temperature, we change resistivity. Typically, the hotter something is, the more resistance it has. I've heard it said that if you've got a steady state computer, one way to supercharge would be to drop it into a vat of liquid nitrogen. Make it very cold, so you decrease the resistance, and the charge flows faster. You can speed up. I don't really recommend that, but in theory, it's an interesting idea. Okay, alternate derivation of Ohm's law. So now you can see, delta V, the potential difference is ED, right? So you've got some distance across, so EL, and then substitute that into the Joe equation. So E then would be V over L, right? And then you've got V equals JL over sigma, and then separating out what these things are, right? J is I over A, where A is the cross-sectional area. L over A sigma, it's L over, A 1 over rho, but then the rho pops up to the top. Now you've got V equals I times rho L over A. Okay, and if we have that, rho L over A, then we can see that's the resistance. And this is so in the next slide, so the resistance is a property of material. Resistivity is a property of the material. Resistance is the property of an object. And the resistance depends on the shape of the object. Okay? And the resistance is equal to rho L over A. If we pronounce that rho and then the rest of this la, this is the Rolla equation. I guess if someone's a Balla or they're a Rolla. I don't know if that's a thing or not, but it might help you remember the equation. We have the Joe equation, now we have the Rolla equation. That's how we calculate resistance, and this is a common type of problem to see. So example 1, you have a copper wire at 20 degrees Celsius. The wire has a cross-sectional area of 1 square millimeter and is 20 meters long. So then what's the resistance? So R is Rolla. And then we substitute in rho here, 1.69 times 10 to the negative 8. It's 2 meters long. And this is 1 times 10 to the negative 6th meters squared. And that gives you 3.38 times 10 to the negative 2nd ohms. So that's the resistance of that object. Different from the resistivity of the object. Okay, let's look at example 2. Right, example 2, aluminum and copper wires. They're both the same length. They both have the same resistance. What's the ratio of their radii? RCU to RAL. So we assume that we're talking here, they're wires, so we treat them like cylinders. And so R of copper is equal to R of the aluminum. That means I've got rho copper L over A. Copper is rho of the aluminum. Times length. The length is the same, and so that's going to end up canceling out here. So get rid of that. And then A is going to be pi r squared. So let's do this. Rho copper, rho of the aluminum, is going to be pi r of copper squared over pi r of the aluminum squared. And pi is the same for both cylinders. So that. So then the ratio R of copper to R of the aluminum is going to be the square root of rho Cu over rho Al. So we look this up. We look these numbers up and get 1.69 times 10 to the negative 8. And then this one is 2.75. Right? Computer tip or calculator tip, before you punch this into your calculator, cancel those out. So now you're taking the square root of 1.69 over 2.75, and you get 0.78. Right, so that means the aluminum radius is bigger, and that makes sense because it has a higher resistivity, so you need more cross-sectional area to get the same amount of current going through it. Okay, so moving on. This next example 3, we have a wire resistance length L is stretched to 3 times its original length. What is its new resistance? Key thing here, volume is the same. Right? It's the same wire. We're not magically producing new mass here. So what we can do here, so V is, it's a wire, so it's going to be pi r squared L. So then if I'm going to, if I'm stretching this, that means the area is going to change. So V equals 1/3 of the area, right, the original area, is 3 times 3 times the length. So these two things are the same volume here. So the initial resistance, we're going to say rho L over A. The final resistance, so let's do that over here too, is going to be rho 3L over 1/3 A. Now when I simplify this, I end up with rho 9 times rho L over A. So that is 9 times the initial resistance. So by reducing cross-sectional area, and by making it longer, I'm increasing the resistance of the thing. If I want to decrease the resistance, I have a larger area, larger cross-sectional area, and a shorter length of the object. Okay, temperature dependence. These are what I call the rat and the pat equations, because if you look at the middle, it's like rho A T, it looks like an A alpha, rho alpha T minus T. So what are we talking about here? Rho naught is I guess you could say the original, or some reference temperature for it's the rho naught and R naught are the resistivity and the resistances at T naught. Okay? And then A is some temperature coefficient of resistance. And that can be found in those charts, temperature coefficient of resistivity, that kind of thing. And it's the same for resistance or resistivity. This works either way. And so, example 4, if a copper wire has resistance 18 ohms at 20 degrees Celsius, what resistance will it have at 60 degrees Celsius? So the equation looks like this. Delta R equals R naught alpha TF minus TI. So that's as simple as that. So this is 18 ohms. Alpha, I looked that up in the chart, and I get 4.3 times 10 to the negative third. And the change in temperature is 40, right? 60 minus 20. This turns out then to be a difference of 3.1 ohms. And so RF is going to be 18 plus 3.1, so that's going to give me RF 18 plus 3.1, so it's going to be 21.1. And that's it for this first packet.